maybe like 2 or 3 minutes, something like that?
Maybe after 2-3 minutes we will start.
Okay, okay. Yes, we already have a nice number of participants, I can see, yes.
Can you see my slides?
Yes, I can see.
Okay,
yes,
okay.
we can see.
Shall we start, President?
Yes, I think, yes, we can start. It's 3 minutes past, yes, okay. So,
very good morning, good afternoon, everybody. And I welcome our President ICID, Dr. Marco Arcieri, and our today's speaker, Professor Dr. Wu Wenyong from China. And we have the third presentation today on our webinar series. The theme of the series is Smart Irrigation Management. And today, Professor Wu will be talking about principles and technology of smart irrigation. Dr. Wu is actively involved in ICID works. He is also the chairman of ICID working group on non-conventional water resources and environment protection. So before I invite Professor Wu, I will request our president, Dr. Marco Arcieri, to say a few words.
thank you, Secretary General. Good morning, good afternoon to all of you, and very warm welcome to Professor Dr. Wu Wenyong from CNCID from China. This is a very important, we are having today a very important webinar because it's dealing on the most important principle of smart irrigation. Why it is important to deal with smart irrigation? Because one of the most important sources or means we have to save water is to deliver the right amount of water at the right time in the right methodology using technology like sensors, artificial intelligence, sensors for soil moisture, for weather, for evapotranspiration, and of course the use of controllers which can be automated in order to optimize irrigation, reduce the waste, and increase the yields of crop that that the rural communities are having for their agricultural activities. So this is why I believe this is a very important webinar, and we are, as ICID, we are very keen to give and disseminate this kind of approach. This is why I'm very grateful today to have this opportunity to introduce this very interesting lecture that Professor Dr. Wu from China from Beijing will deliver to us. So I wish you a very nice webinar, and I'll be looking forward to hear from Professor Wu. Thank you, Dr. Wu. The floor is yours. Thank you.
Thank you, President. Before I invite Professor Dr. Wu for the presentation, I will like to brief all the participants that our next webinar will be on 20th of January. Will be on 20th of January. And the topic of the webinar is application of remote sensing in crop water management and water resource monitoring. And this will be delivered by Dr. Hirsch. He is the Chief Executive Officer of Agrocast Analytics Private Limited. So this is on 20th of January. So I request all the participants to participate in this webinar also. Now, for the participants, you can have questions on today's presentation, and you can write your name, email, and question in the chat box. And I will request Professor Dr. Wu, if he has time, then he can answer some of the questions after the presentations. And later on, he can send the replies through email also. So now I will request Professor Dr. Wu to deliver his presentation.
Thank you very much, Secretary General Gupta and President Marco. It's my pleasure to give this presentation in this webinar. So I do some research on smart irrigation for several years, and today I will show my ideas and applications in China. And I hope
Please share your presentation.
Yes. I hope from this webinar we can exchange the idea and to promote smart irrigation within ICID scope. So my topic is principles and technology of smart irrigation. I'm from China Institute Water Resources and Hydropower Research, and also Secretary General of CNCID. So my presentation includes 4 parts. The first part is we look over the water security or the present situation. About 70% of global water is used for irrigation, and also about 80% of population is in critical water insecure, and about 72% in the status of water insecure. So it is a problem for water shortage in irrigation, and also we face the food crisis, and about more than 20% population in the status of crisis or worse. So it is why we develop a smart irrigation and how to make water more productivity and to reach water saving, yield increase, and green production, high efficient and labor saving. And also the labor is also a problem because because the feasible labor is become less and less in different countries. So in such situation, we should use some new technology or Internet of Things or big data or AI or cloud computing to enable traditional irrigation, such as sprinkler irrigation, drip irrigation, pipe irrigation, and canal irrigation to make water more productivity. So it is smart irrigation is also an important part for the production from the strategic advisable group report on smart farming. We can see the water supply and irrigation is an important part in this report. Second, I'd like to introduce some principles of smart irrigation. And in fact, smart irrigation is an important transformation of irrigation paradigm. For traditional irrigation is experience-driven irrigation. The farmers usually observe weather, soil, and the crops manually. And as for smart irrigation, it is data-driven irrigation. We need to monitor, analysis, and operate based on data. So it is very different between smart irrigation and traditional irrigation. So the smart irrigation, the goals or objective of smart irrigation is use less water, produce more food. So I'd like to introduce the smart irrigation briefly in a regional scale and a field scale. In regional scale, it means in the irrigation systems level. So because some irrigation system is very large, as you know, and they have different functions of smart irrigation. The first is matching water and the supply. Water is better water matching water demand and the supply. So it can lead to it leads to a higher irrigation reliability. The second benefit is make higher precision of water distribution and allocation, and can lead to higher water distribution efficiency, and also can lead to higher irrigation uniformation. As you know, higher irrigation uniformation, it means we can produce more food. And also, the third benefit is for smart irrigation, it is can carry out variable control of water and fertilizer to optimize in fertigation and provide the good conditions for plant growth. Then we can reach higher utilization coefficient of irrigation water in by smart irrigation. As you know, the coefficient is is the two can be divided in two parts. The first part is the distribution coefficient. The second part is a field scale coefficient. So it is why we try to develop smart irrigation and do some research. And in a field scale, how to drive the irrigation. As traditional irrigation, we use drip line to drip water into soil, and the field induced evapotranspiration, and then also they have deep percolation. The percolation is useless for the productivity, but sometimes in the past we also use soil moisture sensor to monitor data, but it is point data, and in fact the field soil moisture is variable in spatial scale. So if you cannot put many sensors in the field, because the sensors is very expensive and also easier to be destroyed. So how to get data? It is important to get high resolution data with UVA and satellites. Then use this data to drive the drip line, the control precision control the drip line water supply to supply water. Then we can get very little percolation, and it will lead to feasible soil water environment and a couple of water and fertilizer. Then we can get higher water use efficiency. And what is a framework of smart irrigation? From my research, I think it is comprised of four important technical sessions. The first is phenotype. The phenotype we should clarify what sensitive phenotype in this process. But this is a research process, and we use the phenotype data to establish some models. The second technical session is sensing, crop water deficit sensing. The third one is decision making for water supply. The fourth one is accurate control, automatic control. So this cycle is state-driven cycle. So in every stage, we must get the data format, such as from phenotype and sensing. We must use the water sensitive phenotype models, and from sensing to decision, it is water deficit index mapper will be produced from sensing to decision making, and from decision making to control, irrigation prescription map will be generated to control the equipment, and also the control session will generate rational irrigation instructions to operate the intelligent equipments. So it is all in different stage. We need different data to generate. The third part, I will introduce the 4 technologies. As you know, in phenotype, what is a phenotype? Phenotype is a visible trait and characteristic of living organism, such as shape, structure, size, color, etc. And we can use UAV, airborne satellites, remote sensing to monitor phenotype. What is objective of the phenotype technology session is to understanding what sensitive phenotypes and its quantitative relation with soil moisture and yield. And the crop spectrum can indicate that the state of water deficit, and also it is important part of water sensitivity phenotype. Something wrong with my PowerPoint. Yes. Next slide. From this picture, we can get conclusions that the reflectance of characteristic of water content at different wavelengths are quite different. Such like blue and green spectrum. And the red spectrum, the stress vegetation or health vegetation, the stress vegetation, the refraction is higher than health vegetation, and in near infrared spectrum, it is a refraction of health vegetation is higher than stress vegetation. So we should learn about the different reaction of spectrum across spectrum to different soil water stress. So this is our we did some relations between the soil moisture with normalized digital number of blue, green, and red imaging. So we found that the soil moisture is significantly related to normalized to predict soil moisture. It can be used can be used to qualify the phenotype, crop phenotype. And we did some research on the different phenotype index. We found that there are a good relation, very close relation to water deficit and yield. So just like REOS AVI index, this index and some other, they have a significant, they're very significant relations with soil moisture. So we can use this index to predict soil moisture. And this is, we also found that the combination of different spectral data significant increase the estimation accurate, such as we use multi-spectrum RGB and TIR, the three kinds of spectral data. We can get higher relations with soil moisture. So it is why we use remote sensing data to replace the soil moisture monitor in the field. Then we can get regional variation of the soil moisture, and we can get the regional yield prediction use the satellites and UVI data. Then we can it will be contributed to good matching of water supply and the water distribution into the field. So we can find that we did some experiment. We found that the different vegetation index, we use the GWDR-VI integration index. We found it is if the yield in the highest yield field, it is also induced to higher the index. And if in the field we get the very lower yield, it also we get lower index value. So it means that it is also we can make a relation with water phenotype and the yield, and we can control the crop production with soil moisture. And for sensing, there have three important work to do. Is first we innovate a sensor equipment to higher efficient to get the data what we want, and also we should make the space, air, and ground data assimilation, and also after simulation we must generate water deficit index map. So from our research, we development polarization spectrum optical products, and also some data, also some soil polarize the soil water synthetic aperture radar water UVA. This is the first time we use synthetic polarized radar to measurement soil moisture in UVA. We want to measure water surface soil moisture use UVA, and also why we development polarized spectral products. It is to make the UVA the sensor measurement higher efficient, and make it can work all day, because for traditional UAV you can only work 1 or 2 hours in the middle day, in the afternoon between 12 to 2 p.m. So it is very inefficient. So we must development new technology, and we produce data processing algorithm for UAV, then to get the higher solution data and high efficient measures to get data. And also we want to development. As you know, if you use UAV, it is important. It is a problem to get data. Get data from the UAV. Then you copy it to computer, and then you use software to work with this imaging to get the final data. It is a long time to do. So we and the Professor Han, we developments multiple thread edge real-time processing device and software to enable real-time imaging acquisition, staging, and parameter retrieval. And how? And you use satellites, and also you get UAV data, but how to integrate them? So because the satellite data have a large scale advantages, but it is a lower resolution, but the UAV have a local scale, a very local scale, very small scale, but they have a higher resolution advantage. So how to match in these two advantage in different level? So we use touch up upscaling method, and to improve the prediction of accuracy of soil moisture. So as this is the first one is original satellite soil moisture distribution map, but the second one is soil moisture distribution map under the touch-up method. So we found that the relation with soil moisture increased more than 30% with different with the touch-up method. So it is important in the integration of different data, such like satellites and UAV and groundwater monitoring data. So, and then we can get the water deficit index map from the data by the previous measure sensory. and use the model to get the final water deficit index. So after we get index, water deficit index, we come to the decision making. In decision making, we should develop three method or we should show three technologies. The first one is you should establish intelligent decision model. The second one is platform. We should development platform and software, and also we should learn about what is the data transform architecture, the cloud and edge device architecture for a data driven. So we development intelligent decision model, and to calculate irrigation prescription map. The model is comprised of several parts. So first we should first is a satellite retrieval model, and after we treat this imported water deficit import data map data, and then we use water balance model to calculate the net irrigation contours, and then we get the final irrigation water contour. So and in finally in time and spatial scale, we get regional irrigation prescription map as a data output of this intelligent decision model. But this process is a complex process. So we did there a lot of computation for regional irrigation district, and also we development decision system. The decision system structure, including the data import, also a system conditions, crop type map, soil textures, weather forecasting, also growing conditions, biomass, etc. Then finally we get the decision processing to generate what deficit index, irrigation prescription, and also smart irrigation prediction. So let's look through the software we development in China, and also it also in operation, in use by a local authority and farmers, but it is only a Chinese version, but we can have a look. We in this software we dynamically show that every day predict in the future in 7 days water deficit index map, and also water prescription map in a week, because we can get 5 days satellite data, so we don't set too long prediction durations. So, and also we develop the smart irrigation app for farmers or for local technicians. They can use the smart irrigation app to learn about the dynamic data in their field, and also they can use to guide the farmers how to irrigate crops. So final, it is very important how to circulate this data. So it is important we should establish cloud, edge, and device architecture for data acquisition, circulation, and execution. So in cloud level, we should establish cloud platform, and in edge, it is we should use. We also develop irrigation edge computing gateway, because for a large irrigation district, it is all we need a higher computing power, and also you need a very protocol compatibility to connect different kind of equipment from different companies. So it is very important to establish a feasible architecture in the system. But I think the cloud platform is the data is serviced by companies. I think it is not. It doesn't mean every project need to develop their own cloud platform. So this is can be provided by professional companies or professional institutes. And also for the control section, it need to solve the three technology problems. The first is irrigation water distribution model. The second is water metering and control. The finally technique is fertigation. So as you know, for a large-scale irrigation system, it is very complex canals. It owns very complex canals or pipeline. So how to distribution water as you want by data. It is important to establish a professional model for irrigation water distribution to realize a rapid and cost-effectively modeling. Then it will help effectively water to deliver water to the fields. And we development a gray box model. It only need less than 5% of parameters required to compare white box model. And the water level forecasting error is less than 6%. Also, water metering is very important in irrigation water distribution. So here you can look at video. China also import some very modern control and metering equipment from development country, but we found this in some scenarios. So we found it is problem that because in China we have different water distribution situation with the other countries where the equipment was development. We find some very hard meeting before the metering box, metering SRAM. So it cannot meet get higher accurate meter water. So also in Yarra River irrigation district, we also face the sediment in the SRAM. So it is a very important, a very problem. We development ultrasonic metering equipment. Then, just like we use the equipment control before and the metering after the control gate. So it can solve the problem the deposit in front of the sediment clogging the flow path and to affect water metering. Also, in the field scale, you must couple the water and the fertilizer together to supply to plant root. So it is, and we develop intelligent fertigation machines to ensure the irrigation control and the precision injection, filter control and pressure regulation. Also, we develop intelligent electric valve to deliver water and fertilizer to field as water precision map, as a data water precision map. So it is a whole system. It is here. This is edge. This is terminal device. So it is important to in development such intelligent machines. It is important to make the data to circulate between different equipments. So as a final, we get we use the fertigation model in the fertilizer machines. Then we can get to match water and fertilizer to get higher WUE improvement, about 12 to 30%. And smart irrigation application in China, we have did some applications in 4 provinces in China, in North China. So we get increased by more than 15% crop yields increased by more than 15%. Also WUE increased by more than 20%. So smart irrigation leads to 3% to 25% of irrigation water, self-irrigation water. And we can find the smart irrigation introduce a higher plant height, more than 20%. Also use a smart irrigation, we can get a higher canopy coverage. It is why we get higher yield compared to traditional irrigation. So also tell some informations about the smart irrigation. I initiated the establishment of smart irrigation AHG in ISO TC 347 at Jovin agro food system. I expect more ICID members and interested experts to participate in the international standardization in operation after this AHG operation. So finally, I want to tell you that what is a smart irrigation system? I think it must be comprised of the following factors, such as it must be big data supported and model algorithm, platform app, and intelligent equipment. So it needs some new technology to enable traditional irrigation to get higher output. A conclusion that smart irrigation driven by data acquisition, circulation, and execution is the most important strategy to deal with worldwide water shortage and food security. And also the combination of mechanism, big data, and intelligent equipment leads to higher and effective decision and control accuracy. Also, disruptive technology will help make smart irrigation great development potential to reach make smart irrigation reach a great development potential in the future. This research is funded by the national project. I also show my thanks to all participants in the project. Thank you very much. My presentation is over.
Yeah. Thank you, Professor Wu, for the wonderful presentation. It was very, very comprehensive. And if there are any question, then you can answer these questions if you see in the chat box, if there is any question. Otherwise, I have a very small question.
Secretary General, there is a question from Nepal.
Okay.
They are asking, given the lack of measurement technology, data availability, and limited technical capacity of the staff, how can smart irrigation be implemented potentially in Nepal? So this is interesting question. Where to start? The question is, how can we start? Professor Wu.
Yes, I think first because the smart irrigation is a very new and new technology, also international frontier technology in the world. I think this smart irrigation we divided it in 3 stages. The first stage is based on a field scale. The third stage we can expand to a regional scale, because in field scale you can realize in a very lower investment and lower data requirement. You can get some benefits and observe some observed data to further development smart irrigation in a larger scale. The first, then also in the second stage, I think if you get enough research background or data, then you can development a regional scale system. As you know, in China, it is the government is pay more attention in smart irrigation, and the government found many projects in this area. So first of all, I think the smart irrigation technology will be driven by companies, also by government. So it is. I think it will be put into a large scale practice in China, maybe 5 years. I think it will be very soon, just like smart farming here in China, development very quickly. So, but in Nepal, I think maybe they have not so good condition in data, in data resource. But I think for remote sensing, satellite remote sensing data, you can get from the European Union. The Seychelles satellites data is enough for us. We also use Seychelles satellite data, and also we did, from my opinion, the UAV is also not. We don't need a very expensive UAV. We need only some effective crop spectrum data. So from my opinion, the UAV doesn't need very expensive UAV. Then it is important you have to do some work to integrate the data from UAV and the satellites. But
Thank you.
I think this technology we have done, it is same. I think in some certain we can exchange in the scope of ICID. We can cooperation in the future.
Yes, exactly.
It is why we started this webinar.
Yes, exactly. That's what I was going to say. This is the role of ICID. This is what we are here for, to share, disseminate, and help other young researchers and technicians to gain from this very important and highly developed new approaches, how to focus and how to scale in the respective countries. So I would invite all the people who participated to this webinar to get in touch with our center office, with Professor Wu, of course. As you can see in the chat, some people also from Africa, they are asking if there is possibility to participate to this training program, how does it work, and so on. So I think because of the questions we have received, I think we hit the spot. I mean, we reached the goal that this webinar has been conceived for. Yes, yes, please.
I Dr. Marco, I said some words about the sharing, the knowledge sharing, because we will develop smart irrigation models. It is a serious model. After we finish the development, I think we can did some training programs for all the members. Then you needn't develop again. You can use. Put in the data, and then you can get the result. I think it will be finished in the. Actually, this model is in operation, but it is not. It's not good face to face to them to operate.
Yes, of course.
We can finish maybe in 2026. then I will connect with central office to whether we can do some training program.
Okay, there are some other questions I see in the chat, but unfortunately, I'm sorry, I need to go to another meeting now, starting in a few, no, already started. So I will leave it to Secretary General. I can only say on my side that I want to thank again Professor Dr. Wu for this very interesting presentation and for the availability to share this knowledge in the future with training programs, of course, under the auspices of our organization of ICID. And I will leave you now, and I wish you all a very nice day. And Secretary General, the floor is yours for the final conclusion. Thank you. Thank you very much. Bye.
Thank you, President, for being here and for your nice words. And see you in the next webinar also.
Yes, of course. Thank you. Thank you.
See you.
Bye.
Professor Wu, can you see some more questions? If you want to answer some more questions, if you can see in the chat box, then you can answer.
The normal questions I have put in what requirement. Oh yeah, it's a question from Abdelham. He asked some question about what requirement evaluation. We use what requirement it is. We use crop model to estimate predict what requirement. It uses the potential evapotranspiration and use coefficient use crop efficient coefficient to get the water requirement. But it is important that you must get. It is important that how to calculate the K. As you know, K is coefficient of is important coefficient. If you use the fixed K, maybe it is not accurate for your model. But we use crop model to combine with the satellite data to simulate a very dynamic K coefficient related to his crop growth. So it is will improve the prediction precisions. So it is we don't calculate the dynamic K coefficient use AI model in this in the calculation of the coefficient. Yes.
Yeah.
This is the final question.
Yeah, there is one question from my colleague. Yes.
Yeah. Hello.
Yeah.
Hello, Dr. Wu. Can you hear me?
Yes. Yes.
First of all, thank you for your very interesting presentation. Out of curiosity, I have a few questions. That you must be estimating the evapotranspiration or the soil moisture either through some UAV-based sensors or maybe satellite also. So what is the relative accuracy between UAV-based observations and the satellite? And do you make a grid out of that? And if so, then what is the resolution of the grid?
You mean the prediction error?
Yeah. Suppose you have calculated evapotranspiration or estimated evapotranspiration using a grid that was made out of observations from a UAV installed sensor.
Yes.
The other grid might be from satellite-based sensors. So what is the comparison between the two data sets you have? Which is more accurate and which is useful for which region and which is useful for other reasons?
Yes, we use touch-up upscaling method to integrate the data from UAV and satellites. It is significantly increase the prediction accuracy and more than 30%, more than 30%. And I think the prediction error after improvement is less than 10%. Less than 10%.
Yeah, and what is the grid size? Resolution?
Grid resolution.
10 meters.
Yes, for UAV, it is several centimeter. The scale of centimeter. For the satellites, it is 10 meter.
Okay. Right.
Yeah. It is very interesting work here. I think maybe we can discuss in detail in the future.
Okay, thank you.
Just out of curiosity, I would like to know how much area is still you have under smart irrigation in China?
No, not very large here in China, because this technology also it is a new technology in China. But as you know, China produce most of UAV, so maybe it will be developed very quickly in China. Also, the government also pay much more attention in this field. So I think it will be regional use. Here now we have our technology have used to 4 provinces. I think in the decision making level, we can use the much larger scale in China. Then it is difficult to match the intelligent equipment with irrigation decision, because intelligent equipment need much more investment and it need time to contribute to build up. So first of all, I think we should tell farmers, tell the agriculture companies how much water it is better it is feasible for crop in different stage, and then in the future infrastructure construction, more and more intelligent equipment will be used in the future. So it is a different step. Also, smart irrigation should I think it is in different level of smart irrigation. Also for in practice, it's also a step by step. So in different stages, the technology, the most important technology is different, I think. So it needs a long time, but it is very important. We should do.
Yes. And I agree with your idea that we should go for trainings also. If we go for trainings of young professionals in smart irrigation, so we can we can plan that in next year. We will consult each other in that matter. And so, shall we conclude now, Professor Wu? It was a really excellent presentation and very, very comprehensive, very educational, and we learned a lot. I think all the participants enriched themselves by this presentation, and we are grateful to you for giving this presentation on this platform. And we hope that in future also you will be delivering the talks on smart irrigation management webinar and other webinars also. So from ICID Central Office and on behalf of all the participants on this webinar, I thank you very much for giving this presentation. So I thank you all the participants for joining this webinar. And our next webinar will be on 20th of January. And this will be on application of remote sensing in crop water management. And this will be given by Dr. Harsh Shah. He is CEO in Agrocast Analytics Private Limited. So see you on 20th of January. Thank you very much. Thank you.
Gupta.
Good.